Hello, Math 1060 class. I want to do the problems from the expected value section, starting with number 1. If a game has expected value 0, then the game is called blank. The answer is fair. A game in which the expected value is not 0 is called a blank game, unfair game. Some basic terminology. Your insurance company has a policy to insure personal property. Assume you have a laptop computer worth $2,500, and there's a 3% chance the laptop will be stolen during the next year. What would be a fair premium for the insurance? Well, on these kind of problems, you just have to find 3% of the value of the merchandise, because on average, that's how much money will be lost because of theft. So let me use a calculator. I get $75. So the insurance company will probably charge a little bit more than that because they have to make a profit, but $75 is the answer. Consider a game in which a player rolls one die. If an even number comes up, the player wins the number of dollars shown on the die. If an odd number comes up, the player loses the number of dollars shown on the die. Calculate the expected value for the game. Is it fair? So this is the first problem where we have to find the expected value of a game. So the idea is the expected value is defined to be the probability of the first outcome times the value associated with that outcome, plus the probability of the second outcome times the value associated with that outcome, all the way down to the nth one. So that's the definition of expected value. Now remember, in this problem, we're rolling just a single die, so there are 6 possible outcomes. We could roll a 1, 2, 3, all the way up to 6. So let's see if we can figure out the expected value of the game. Well, the probability of getting a 1 is 1 out of 6. And it says if an odd number comes up, the player loses the number of dollars shown on the die. So we would lose $1 if we got a 1, and I'll put that right there. But we might get a 2. The probability that we get a 2 is also 1/6. But it says if an even number comes up, the player wins the number of dollars shown on the die. So we'll indicate that with a +2. The probability of getting a 3 is 1/6, but we're going to lose $3 if we roll an odd number that's a 3. And just keep going. We could get a 4. If we get an even 4, that means we win $4. Probability of getting a 5 is 1/6. We lose $5. And lastly, the probability of getting a 6 is 1/6, and we would win $6. So plug all that into a calculator. Let's see what we get. I get 0.5. So it sounds like the expected value is 50 cents. And is the game fair? The answer is no, because the game is only fair if the expected value is 0. That's the definition of a fair game. The expected value has to be 0. A certain game consists of rolling a single fair die once again. If a 4 or 5 comes up, you win $8, otherwise you lose $4. Find the expected winnings of the game. So it sounds like in this case we just have 2 possible outcomes. We're either going to win or we're going to lose. But if a 4 or 5 comes up, you win $8. Well, what's the probability of getting a 4 or 5? That's 2 out of 6 numbers. And if that happens, we win $8. Otherwise, you lose $4. That means if we get a 1, 2, 3, or a 6, we would lose $4. And the probability of this is 4 out of 6. That is the expected value of the game. Let's plug it into a calculator. I get 0. So this is a fair game. It means in the long run you don't lose or gain money. Therefore it is fair. A card is drawn from a standard 52 card deck. Calculate the expected value for the game. A player must pay $9 to play the game, which must be subtracted from the winnings. If a club is drawn, the player wins $16, otherwise they lose their $9. Calculate the price that would make the game fair. So first of all, we have to calculate the expected value. And once again, we're either going to win or we're going to lose. And there's only one way to win, and that's if we get a club. So how many clubs are there? 13 out of 52 are clubs. That's the probability of getting a club. But it says, if a club is drawn, the player wins $16. So it's kind of tempting to just put 16 in parentheses, but it says a player must pay $9 to play. So you really have to subtract the amount that you paid to play from your winnings in that first term. Now, what's the probability we don't get a club? Well, there are 39 out of 52 that are not clubs. Excuse me. So what happens if we don't get a club? Well, it says if we don't get a club, we just lose our $9. So you can think of that as 0 minus 9. We just lose the money that we paid to play. So I get -5 for the expected value of the game. So you want to stay away from this game because on average you're going to lose $5 every time you play. And what would be a fair price of the game? Okay, well let me show you something. Here's how you calculate the fair price. You're supposed to add the expected value that you just calculated to the price to play the game. So in this case, we found the expected value was -5, but we actually paid $9 to play. So the price that would make it a fair game is $4. Remember that little formula. For the past several years, a fire department has been keeping track of the number of fire hydrants that have been opened illegally daily during the heat waves. And they give us a little table. All right. So in the first column, 20, 30, 40, 50, 60, 70. In the second column, 10, 15, 6. These are my numbers. 8, 9, 3. Use the information to calculate how many hydrants the department should expect to be opened per day during the coming heat wave. So it doesn't look like an expected value problem, but it really is. You're looking for the expected number of hydrants opened per day. So let me show you how to do this one. Now, the first thing you want to do is add the total number of days together. And I get 51. So notice that 10/51 of the time, whatever that percentage is the percentage of the time that 20 hydrants are opened in a day. So you can kind of think of the 10 over 51 as a probability. So there is a 15 out of 51 probability that 30 will be opened. So once again, use that formula that says the expected value is the probability of the first outcome times the value associated with that first outcome, all the way up to the nth one. So I'm going to put in the numbers here in a second. Well, what's the first probability? It is 10 out of 51. And the value associated with that is 20. Second possibility, is that 30 fire hydrants are opened, and that happens this percentage of the time. So it would be 15 over 51 times 30. And we'll keep going like that. 6 over 51 times 40. 8 over 51 times 50. 9 over 51 times 60. And 3 over 51 times 70. Let's plug all that into a calculator. And I get 40. So on average, we would expect about 40 hydrants to be opened per day during the upcoming heat wave. So kind of a nice example of expected value that was a little bit different than some of the other ones we did. Here's another nice example. Assume an investor has $14,000 to invest in precious metals. Use the table to calculate the expected gain or loss. So let me give you the table that I'm given. So let me explain this table a little bit. It says that the probability that we gain 11% of our money in profit is 0.41. The probability that we break even is 0.15. And the probability that we lose 21% of our investment is 0.44. And keep in mind that we're investing $14,000. So let's calculate the expected gain or loss, which I'll just write as expected value. So notice in this case there are actually three possible outcomes. We could gain 11%. The probability of that is 0.41. So how do we decide what the value associated with that is? Well, we just have to figure out what 11% of 14,000 is. That's how much we're going to gain in that case. The second possible outcome is that there is no change. That means we don't gain or lose anything, so put a 0 there. And the third possible outcome is that we lose 21% of our money. So make sure you make it a negative and just take 21% of 14,000. Just put a negative sign there. So let's see if we expect to gain or lose money in precious metals. It sounds like we're going to lose money on average. By the way, this one says round to the nearest whole number, so we'll make that negative 662. So kind of an interesting application of expected value. One more problem. Let's do it. 700 chances are sold at $3 a piece for a raffle. So you have to pay $3 to play a raffle. There's a grand prize of 400, 2 second prizes of 250, and 5 third prizes of 100. First, calculate the expected value of the lottery. Determine whether it is a fair game. If it is not fair, determine a price for playing the game that would make it fair. So we have a grand prize of 400. We have 2 second prizes of 250. Five third prizes of 100. All right. So actually there are 4 possibilities in this case. You could win the grand prize, the second prize, the third prize, or nothing. So don't forget the nothing. So when we calculate the expected value, you actually have 4 possible outcomes. Well, how many tickets did we sell? It says 700. 700 tickets total. So we just have one grand prize winning ticket. That means the probability of winning the grand prize is 1 out of 700. So what is the value associated with that? Well, we win 400, but don't forget we had to pay $3 to play the game. So you've got to subtract that from your winnings. Now we have 2 second prizes. So that means you have 2 tickets that are $250 winners. But again, subtract the $3 from your winnings. We have 5 third place winners. We only get 100 for that. And this last term is the one that's easy to forget. You have to also consider the possibility that you might lose. And that's actually going to happen most of the time. So how many winners are there? 5 plus 2 plus 1, it looks like 8. That means there are 692 losing tickets out of 700. And that means you just lose your $3. You don't win anything. So you can think of that as 0 minus 3 if you want to. So a little complicated to put all that into a calculator, but just use parentheses. Give me a second and I'll do it. I get -1. So on average, you're going to lose $1 every time you play this game. If the game is not fair, and by the way, it is not fair because the expected value is not 0, determine a price for playing the game that would make it fair. So let's use the formula that I mentioned a couple of problems ago. The fair price is the expected value plus the price to play, the original price to play. And we just found the expected value was -1. It costs $3 to play. That means $2 would make this game fair. So if the tickets were $2 a piece instead of $3 a piece, in the long run we would break even instead of losing $1 on average.